Okay. Hello, everybody. My name is Liam. I'm a PhD student at the Guy's Group, conveniently. And today I will talk to you about a project that we do in the group. Usually we develop methods to treat quantum systems, and this is one of the methods, which is essentially this stochastic representation of wave functions, which allows us to do derivative and determinant-free schemes, which I will show you soon enough what it means. So essentially, the main problem that we want to tackle is solving Schrodinger's equation, right? And we want to find the eigenstates and energies of a given Hamiltonian. Usually, what is interesting is the ground state energy and wave function. And as we all know, it's not solvable analytically for larger systems in the hydrogen atom or a few other specialized systems, and numerical methods are necessary. Now, direct approaches are also not really viable because of the curse of dimensionality, where if we try to solve some Hamiltonian on a grid in very straightforward manners, we quickly need exponentially more resources, memory, and CPU time if we want to calculate these things. So we need more sophisticated algorithms to do that. A very common trope that people use in their methods is the variational principle, where we always know that for a given guess of a wave function, if we calculate its energy with a given Hamiltonian, we will always get an energy which is higher or equal to the ground state energy. This allows us to essentially, say, have a guess of a wave function that is parameterized with some parameters, and then we can play with those parameters until we find minima over this energy landscape, which is defined within this parameter space. But then the problem becomes an optimization problem, where we need to find the best energy given a lot of changes that we need to apply to this set of parameters. Now the optimization problem is maybe fine enough in one dimension like here, but if we have many parameters, say if we want to use a neural network as an ansatz, and we have tens of thousands of dimensions in this parameter space, this NP-hard problem really becomes untreatable, and stochastic gradient descent methods don't cut it anymore. Something more sophisticated that people do is essentially imaginary time propagation, where we know that if we start with a wave function of with a given energy and apply the imaginary propagator, for long enough imaginary time, we should collapse to the ground state wave function. This can be done in the parameter space. This is called stochastic reconfiguration. But the problem then becomes that we need to apply this inverse of a matrix that has the size of the per number of parameters, which has the cost which is cubed with the number of parameters. Meaning if we want to use a neural network with 70,000 parameters, it becomes quite a challenge. And our stochastic representation, which I will present shortly, is essentially the solution to this kind of problem. So let's say we have some guess that we want to optimize now. It can come from some Hartree-Fock solution or perhaps even a random guess toward the wave function. And then we want to propagate it in imaginary time. So instead of propagating the entirety of it, we can propagate only a set of samples. So we can choose by some scheme the samples that we want to evaluate the wave function in the future imaginary time at, apply the propagator only for these points. I will immediately show you how we can do that, and then get these pairs of positions and the value of the wave function in the future imaginary time. After that, we can do some interpolation technique to get the evaluation of the entire wave function in all of the space in the new imaginary time. This can be done with some simple regression algorithms or machine learning, but now this is a supervised task. We need to only do regression, not optimization anymore. We don't look for the minima of the energy. Repeating this procedure many times essentially should propagate the wave function in imaginary time, and we should collapse to the ground state wave function, as can be seen here with the harmonic oscillator in one dimension. And this transformed the optimization problem, which is really hard, to many smaller regression problems, which is more approachable, perhaps. Now, the one question is, how do we propagate even the few samples that we chose for this procedure? So in the first paper about this, we essentially applied the Taylor expansion of the propagator in short imaginary times, which worked quite nicely, but soon enough we encountered the problem where if we wanted to use neural networks that are not differentiable everywhere, say if we use activation functions that are not as smooth as you might want, applying this kinetic energy operator, which is the derivative in the positions, it doesn't behave very nice. So we wanted to find an alternative to this that would allow us to use more ansatzes. Here comes the way the propagator, we can describe it using a path integral. So we can do a path integration over a short time, and by summing over paths from the previous wave function, which essentially requires evaluation of the previous wave function at many positions, we can find the value of the wave function at the new point without ever needing the wave function to apply derivative onto it or for it to be smooth or any kind of other limitation. So essentially we can do this with Monte Carlo, which is an immediately parallelizable task. So if we repeat this many times, we can do the propagation without any derivatives and without any limitation to our ansatz. So this is essentially the stochastic representation part. Now off to the determinant free part. So as we all know, usually we need our physical particles or bosons or fermions, which exhibit special symmetries, right? Bosons are symmetric to exchange and fermions are antisymmetric to exchange. Now for bosons, many solutions already exist because the ground state wave function is always positive and we don't have any nodes that cause issues with the common methods. But for fermions, usually we must have a sort of a determinant in our ansatz. Usually a Slater determinant where we have a basis set of some orbitals, or sometimes it's more sophisticated when we have van der Monde ansatzes, but essentially the cost is cubic or squared with the number of particles. So if we have many such determinants or many particles, it becomes quite a limit in all problems that do such a thing. Our approach allows us to do something quite different, which actually almost removes this cost entirely, where we symmetrize the wave function by a sort of a sorting algorithm. So instead of storing the wave function in the entirety of space, we can only store it in the part where we essentially copy it over the nodes, right? Because in this case, for example, we have two particles in one dimension. We have the positive part and the negative part. It's antisymmetric to exchange of particles. And instead of storing the entirety of it, we can store only this part. So what we do is we only store the part where x1 is smaller than x2, only this area. Now say we want to do this integral that I showed you before, and at some point we need to calculate the value of the wave function at this position, where x1 is bigger than x2, right? These are the values, 0.6 and 0.2. All we need to do is simply apply a sorting algorithm and add a minus sign, which is the permutation that we just did, and get the value that we had all of the information about in the other side. So all we applied is a sorting operator, which has a cost of n log n, with a much smaller prefactor. And this essentially removes entirely the need for a determinant and removes this inherent cost that we always had in such methods. So this is the determinant free part. And now off to some few results. One last thing. Comes the question, okay, this is nice, but why couldn't we have done that without the path integrals? So in these nodes where we do the optimization, because it's such a brute force matter when we just copy and paste with a negative sign, at the nodes we could have had discontinuities as seen here, which will disappear at some point after we propagate in enough imaginary time. But if we need for the propagation to apply a derivative, this area would have a kinetic energy of infinity and the algorithm would not be stable. The path integration completely avoids this problem, which makes this solution applicable. So we tried this for up to 10 particles in a 2-dimensional harmonic oscillator, so a 20-dimensional system in continuous space. And we checked how the fidelity compared to the exact result is. And we saw essentially that it fluctuates around 1, and the infidelity increases, but sub-exponentially, which is a quite promising result because the fidelity is really a very delicate number that can get destroyed very, very fast. And the fact that for such high-dimensional systems, it did not get destroyed, it's quite hopeful. Another thing that we showed with this is that not only fermionic and bosonic symmetries can be applied, but also any special symmetries that we want. For example, hexagonal or pentagonal symmetries. So this allows us to see, here you see the electron density for 6 fermions in a harmonic oscillator, but now with increasing interaction. And this allowed us to see a nice Wigner transition where the electrons become localized in space thanks to the interaction between them. And we could not have done that without actually enforcing this kind of symmetry, because otherwise we would just see some nonsense, as the wave function can collapse to many combinations of the ground state, which has a round symmetry. And enforcing the actual pentagonal or hexagonal symmetry allowed us to see it much more clearly. One last thing, how all of this connects to the topic of the day, is that essentially what I did here is propagating a state in imaginary time, but we can also do this in real time, right? We could change the Hamiltonian to the Hamiltonian that is appropriate for the gate that we want to apply. And since the quantum, the qubits is essentially a system which is smaller than the continuous system that I showed you, it should be applicable and might even be easier. The only question is how does this method work in real time, which is yet to be done, but it should work at least for short times unless the sign problem becomes too major. So this is essentially it. We showed you here an alternative to normal variation Monte Carlo, where we have much more freedom in the choice of our ansatzes, with essentially no limit to what we can do. This could be any neural network or ansatz that you can think about, and it should be applicable with this method, also with very nice application of symmetries. So thank you for the organizer for accepting me.